A storm is brewing in the Atlantic. It's not just any storm, but something larger, more powerful, something that could rival the biggest storms ever recorded. As meteorologists keep a close eye on this rapidly developing system, experts are scrambling to understand the full extent of its potential. Could this be the one we've all been bracing for? The big one? The storm that has the potential to rewrite history? For many, it's a question on the lips of anyone living along the eastern seaboard, from the United States to the Caribbean, and across the ocean to Europe. The sheer scale of this system is unlike anything seen in recent years, and its rapid intensification has caused alarm across the scientific community. There's something uniquely ominous about the way storms like this one develop. Meteorological patterns that once seemed predictable are becoming more erratic, with the early stages of this storm suggesting a level of intensity that could potentially be catastrophic. The signs are there: unusual atmospheric pressure readings, rapidly changing sea surface temperatures, and a surge in atmospheric moisture, all of which contribute to the perfect recipe for a massive storm system. But it's not just the strength that has experts on edge. The trajectory of this storm is also a cause for concern. With the Atlantic Ocean seeing increasingly volatile weather patterns over the past few decades, the path of these storms has become far more unpredictable. While traditionally, hurricanes in this region follow a relatively set course, this particular storm seems to be defying the norms, leaving meteorologists unsure about where exactly it will land and what kind of damage it will leave in its wake. As we watch this massive system grow in power, the question arises: what exactly is causing these storms to form with such intensity? And why does it feel as though we're on the brink of something much more devastating than usual? It's time to break down what's happening, step by step, and explore why this storm has the potential to be unlike anything we've seen before. The first thing that stands out about this storm is the sheer size of it. It's not just a small, localized system, it's massive. It spans miles across the ocean, and its cloud cover alone reaches hundreds of miles in every direction. While storms of this scale are not unheard of, the rapid development and growth of this one is what has scientists truly alarmed. The most concerning part? The way it's intensifying at an unprecedented rate. In just a matter of hours, this system has gone from a modest disturbance to a Category 3 hurricane, a classification that typically takes days, if not weeks, to reach. Some storms grow gradually, slowly gaining strength as they move across warm ocean waters, but this one seems to be skipping the usual stages of development altogether. The most concerning thing is the rapid intensification. We've seen this happen in the past with some of the most destructive storms in history, and the fear is that this one could follow the same path. Experts point to the increasing sea surface temperatures as one of the main culprits behind the storm's rapid intensification. Over the past several decades, the temperature of the Atlantic Ocean has risen significantly, fueled by global climate change. Warmer water provides more energy for storms to feed off of, accelerating their development. What's more troubling is the fact that these higher temperatures are now being coupled with changing ocean currents, leading to more volatile conditions. Scientists have observed that warmer waters are now extending deeper into the ocean than ever before, creating a larger pool of energy for storms to draw from. This unprecedented increase in ocean heat could be contributing directly to the storm's rapid intensification. As the storm's center moves over these warm waters, it gains strength exponentially, making it more dangerous with every passing hour. However, it's not just the warm waters that are a cause for concern. The atmospheric conditions are playing a major role as well. Over the past few years, weather patterns have become less predictable, with atmospheric pressure systems becoming more unstable. This current storm is exhibiting the classic signs of an unusually deep low-pressure system, which essentially acts like a vacuum, sucking in more and more air from its surroundings. This causes the storm to strengthen rapidly, pulling in not just moisture but air from the upper atmosphere as well. The interaction between these different layers of air can result in massive storms that escalate to hurricane-strength winds in a fraction of the time. What's even more alarming is the storm's behavior once it reaches the coast. Historically, storms of this size tend to veer off to the northeast and dissipate before making landfall. However, the current atmospheric conditions suggest that this storm may follow an entirely new and unpredictable path. Experts are warning that it could make landfall in unexpected areas, potentially leading to catastrophic flooding, high winds, and dangerous storm surges. If it continues on its current trajectory, it could strike key population centers in the Caribbean, the Gulf of Mexico, and the southeastern United States, possibly even causing devastation in cities that are rarely affected by such storms. This unpredictability is at the heart of what makes this storm so terrifying. While hurricanes are, by nature, difficult to predict, the increasing frequency of extreme weather events has made it all the more challenging to model their paths accurately. Advances in technology have certainly improved our ability to track storms, but with storms like these, growing at an exponential rate and changing direction unexpectedly, predicting their exact impact remains a significant challenge. Meteorologists are also studying the way the storm is interacting with the atmosphere and ocean currents. As storms like this one intensify, they can influence the surrounding weather patterns, creating a feedback loop that exacerbates the situation. For example, as the storm grows stronger, it begins to pull moisture from the atmosphere in increasingly large quantities. This creates intense rainfall in surrounding areas, which can then lead to flooding, particularly in low-lying regions. In addition, the increased moisture in the atmosphere contributes to the formation of more clouds, creating an even stronger storm system. Scientists are also keeping a close watch on the storm's potential to spawn tornadoes. Historically, large hurricanes and storms of this nature have been known to trigger tornado outbreaks, particularly in the outer bands of the storm. The unique atmospheric conditions associated with this system make it a prime candidate for spawning tornadoes, which could cause widespread destruction far beyond the immediate hurricane path. These additional hazards make this storm one of the most dangerous systems to watch in recent memory. As the storm continues to develop, the question remains, will this be the big one? Will it be the storm that breaks records, wreaks havoc, and reminds us all of the power of nature? While no one can predict the future with certainty, the fact remains that we are witnessing the formation of something extraordinary. The combination of rapid intensification, unpredictable movement, and unprecedented strength make this storm one of the most dangerous and fascinating weather systems to emerge in recent years. As we continue to monitor this evolving situation, it's important for all of us to stay informed and be prepared for whatever may come. The power of nature is undeniable, and it's up to us to respect and respond to it accordingly. One of the most intriguing potential causes behind this rapidly intensifying storm is the unusual shifting of ocean currents. For years, experts have been monitoring the Atlantic Meridional Overturning Circulation, AMOC, a large-scale ocean current system that helps regulate the climate. The AMOC is essentially a giant conveyor belt of water that moves warm water from the tropics toward the North Atlantic, where it cools, sinks, and then flows back toward the equator. This circulation plays a critical role in shaping weather patterns across the Atlantic and beyond, and its disruption could have massive consequences. Lately, however, there have been worrying signs that this circulation is slowing down. And this slowing could be having a significant impact on the intensity of storms, including the one currently forming over the Atlantic. When the AMOC weakens, warm water from the tropics doesn't get pulled northward as efficiently. This disrupts the balance of ocean temperatures, potentially causing an increase in heat retention in the tropics. As a result, storms that form in the region could feed off of unusually warm waters, growing at an accelerated pace and becoming far stronger than usual. It's not just a small change either. Scientists have observed that the AMOC has been weakening for decades, with the most significant slowing occurring in the past 20 years. While this shift in ocean currents might seem like a gradual process, its effects on weather systems can be rapid and catastrophic. In fact, research has shown that when the AMOC slows or becomes more erratic, it can lead to more intense hurricanes in the Atlantic. This is exactly what experts are concerned about with the current storm. As the AMOC continues to weaken, it could be creating the perfect conditions for storms to form and intensify much more rapidly than in the past. Think of it like a switch that flips. When the circulation slows down, it's as if the storm is being handed more fuel. Without the usual regulation of ocean temperatures, the tropical waters remain unnaturally warm for longer periods of time, feeding the storm's growth. The storm we're seeing in the Atlantic is not only benefiting from these warmer temperatures but is also being boosted by the erratic shifts in ocean circulation. And, as a result, the strength of this storm is increasing at a pace that is far outpacing historical patterns. What once took days or even weeks to develop is happening in a matter of hours. The most concerning part of this theory is that we don't fully understand how much the weakening of the AMOC will impact weather systems in the future. While it's been happening gradually, the process may be reaching a tipping point. There are many questions that remain unanswered. How much slower can the AMOC get before the impact on storms becomes even more pronounced? Could we be witnessing the early stages of this shift? And is this storm the first of many more to come? There's also the possibility that this shift in ocean currents is not the sole cause of the storm's rapid intensification, but rather one piece of a much larger puzzle. The atmosphere itself plays a huge role in the development of storms, and changes to atmospheric pressure systems could also be interacting with the shifting currents to fuel this tempest. To make things even more complex, scientists are also considering the impact of melting ice sheets in the Arctic. As temperatures rise, glaciers and ice sheets are melting faster than before, which is altering the salinity levels of the ocean. This affects how the water circulates, further contributing to the instability of the AMOC and amplifying the storm's strength. This interaction between rising sea levels, melting ice, and changes in the AMOC is something that's been studied in climate science for years, but we're now seeing these effects manifest more visibly in real time. It's this confluence of oceanic and atmospheric changes that could be giving birth to some of the most intense and unpredictable storms the world has ever seen. With all of this in play, it becomes clear why the storm forming over the Atlantic is so worrisome. The environment in which it is developing has never been more conducive to rapid intensification, and the fact that scientists can't fully predict how the storm will evolve only heightens the sense of urgency. If the AMOC continues to weaken, and if ocean temperatures keep rising, we could see more storms of this nature, storms that form faster, grow stronger, and reach landfall with devastating force. The unpredictability of such a storm adds to the tension, with experts watching and waiting to see how this system will unfold. As the storm approaches and intensifies, scientists will continue to monitor the changes in ocean currents, atmospheric pressure, and see surface temperatures to understand just how much of a role the AMOC plays in such rapid storm formations. And as we move forward, it's becoming increasingly clear that the world's oceans, shifting, warming, and changing in response to human activity, are key players in the storm systems of the future. The question remains, how many more storms like this one will we face as the climate continues to change? It's a powerful reminder of how interconnected our planet is, and how events that seem distant can have far-reaching impacts. The ocean currents, the atmosphere, and the warming planet all create a volatile cocktail for future weather systems, and this storm may just be a glimpse into the future of Atlantic hurricanes. One of the most fascinating and alarming aspects of this issue is the way these shifts in ocean currents are triggering a chain reaction that's impacting weather patterns far beyond what most people would expect. To better understand the implications of the weakening AMOC and how it's contributing to this massive storm, we need to explore the concept of ocean heat content and how it plays a critical role in the development of tropical storms. When you think of storms, you often hear about warm waters providing the energy needed to fuel a hurricane. This is entirely true. Warm waters act as the storm's energy source, and the warmer the water, the more energy is available for the storm to grow. But what's happening now is that the temperatures in certain parts of the Atlantic are rising to unprecedented levels. As the AMOC weakens, there's a backlog of warm water in the tropical regions that would normally be redistributed by the current system. Instead of being carried north to cool down, it stays in place, adding even more heat to the surface waters. Imagine a kettle of water on a stove. The heat builds up beneath the surface, and as the water warms, it becomes more volatile and prone to rapid boiling. This same principle applies to the ocean. When water remains unnaturally warm, it provides an environment ripe for violent storms to develop. But in the case of this storm forming in the Atlantic, the situation is even more extreme. As ocean temperatures rise in response to the weakened AMOC, the storm is able to access an almost limitless supply of heat energy, causing it to intensify faster than ever before. This isn't just a theoretical problem anymore. In 2020, researchers observed ocean temperatures in certain parts of the Atlantic Ocean that were significantly higher than normal for that time of year, which directly contributed to the rapid strengthening of hurricanes like Hurricane Laura. With the AMOC showing signs of continued weakening, the same conditions could be present for the current storm. The question on everyone's mind is, could this storm be the result of the beginning of a trend in stronger, faster-growing storms due to these abnormal ocean temperatures? But even more concerning than the sheer energy available to the storm is the way these temperature shifts are creating a feedback loop. The more heat that is stored in the ocean, the more moisture is evaporated into the atmosphere. This additional moisture acts as fuel for the storm, creating even more intense rainfall and atmospheric instability. The result is a storm system that doesn't just intensify in terms of wind speed, but also in terms of its capacity to generate extreme rainfall and catastrophic flooding. We've seen this phenomenon already in recent years. For example, in 2017, Hurricane Harvey brought unprecedented rainfall to Texas, causing record-breaking flooding. Experts later linked this extreme weather to the increase in sea surface temperatures, a consequence of a warmer-than-usual Atlantic due to shifts in ocean circulation. As these events become more frequent, it's becoming harder to deny that the warming waters, enhanced by the weakening AMOC, are playing a huge role in how storms like the one we're seeing now are developing. What's especially alarming about this is that the scientific community is only beginning to fully understand the long-term effects of this process. While we've had hurricanes for centuries, the speed at which they intensify today is far greater than what we saw in the past. This rapid intensification could become the new normal. If ocean currents continue to slow down, we could see more and more storms popping up out of nowhere and escalating at a pace that is difficult to predict. The storm forming over the Atlantic right now might just be the start of a new era of unpredictable and devastating hurricanes. Adding another layer of complexity is the changing weather patterns due to shifts in the jet stream. This fast-moving current of air high in the atmosphere often guides weather systems, including storms. But as the climate warms and the AMOC weakens, the jet stream is becoming more erratic. In particular, a slower or more meandering jet stream can allow storms to stall over certain areas for longer periods of time, which leads to prolonged periods of extreme weather. This phenomenon is exactly what we saw with Hurricane Harvey in 2017, which stalled over Houston and caused catastrophic flooding. The current storm in the Atlantic could be subject to the same conditions, causing it to linger longer, intensify further, and bring even more devastation to coastal regions. It's not just the tropical waters that are changing either. As the Arctic continues to warm faster than the rest of the planet, it's causing a shift in atmospheric pressure systems that further complicates weather patterns. The polar vortex, which normally remains in the Arctic, has been shifting and dipping further south in recent years, influencing weather in the northern hemisphere. When the polar vortex weakens, it can allow warm air from the tropics to move farther north, which then interacts with cold air masses, creating more extreme weather events. This is yet another factor that could contribute to the development of storms that are not just more frequent, but also more intense and unpredictable. The bottom line is that the rapid intensification of this storm is not just a matter of random chance. It's a reflection of larger, interconnected changes happening in the world's oceans and atmosphere. As the AMOC weakens, as temperatures rise, and as atmospheric conditions shift, storms like the one we're witnessing now are becoming a frighteningly common reality. While we cannot say with certainty whether this particular storm will turn into something catastrophic, it is undeniably part of a larger trend that suggests we're entering an era of more extreme and unpredictable weather events. As we've already established, the ocean plays a massive role in fueling storms like the one currently forming over the Atlantic, but the atmosphere itself is equally important in determining how these storms evolve. A key element in storm development is atmospheric instability, which is significantly impacted by changes in temperature, pressure, and moisture in the air. The most dangerous storms tend to form in environments where warm, moist air from the ocean meets cooler, drier air higher up in the atmosphere. The resulting instability can cause air to rapidly rise and condense, generating the powerful energy needed to fuel a hurricane. This is where climate change comes into play, influencing the environment in ways that are dramatically altering these patterns. As global temperatures rise, the atmosphere can hold more moisture. Warmer air has a higher capacity to retain water vapor, which is essentially fuel for these storms. When this warm, moist air rises and meets cooler, drier air in the atmosphere, the process of condensation releases even more latent heat, further enhancing the storm's energy. But what happens when this process goes into overdrive? You end up with a much stronger and faster-growing storm. Hurricanes that once took several days to intensify into major storms can now rapidly escalate in just a few hours, as the increased moisture in the atmosphere contributes to more violent winds, heavier rainfall, and greater overall intensity. For example, take a look back at Hurricane Maria in 2017. Within just 48 hours, this storm transformed from a Category 1 to a Category 5 hurricane. Experts attributed this rapid intensification to the combination of very warm ocean waters and a particularly unstable atmosphere. In fact, scientists have found that over the past few decades, hurricanes have been intensifying at faster rates than ever before, with more storms reaching major hurricane status, Category 3 and higher, in a much shorter period. But that's not the only factor at play. The jet stream, a narrow band of fast-moving air high in the atmosphere, plays a pivotal role in steering storms, guiding them in particular directions and influencing their strength. Typically, the jet stream helps steer storms away from land, keeping them out over the open ocean where they can dissipate. However, as climate change continues to alter atmospheric patterns, the jet stream has begun to slow down, become wavier, and even dips southward more frequently. This allows storms to stall over specific regions, bringing catastrophic consequences. A prime example of this phenomenon was seen in 2019 with Hurricane Dorian. As the storm strengthened into a Category 5 hurricane, the jet stream essentially blocked its path, causing it to linger over the Bahamas for several days. This meant that areas already ravaged by the storm's powerful winds were subjected to days of relentless rainfall and flooding, exacerbating the devastation. If the current storm in the Atlantic is influenced by similar atmospheric conditions, it could result in a prolonged and disastrous event for coastal regions, with hurricane-force winds, life-threatening flooding, and possibly even tornadoes spinning off from the storm's outer bands. Not only does a weaker or slower-moving jet stream increase the duration of these storms, but it can also create a phenomenon known as storm training. When storms stall or move in a series of loops due to jet stream anomalies, they can follow a repetitive path over the same areas, leading to a compounding of rain and wind over a single location. This was a hallmark of 2017's Hurricane Harvey, which unleashed catastrophic rainfall over Houston, Texas, as the storm stalled and retraced its steps multiple times. While not every storm will behave in this manner, the increasing unpredictability of weather systems due to a destabilized jet stream makes it a real possibility for future storms. Looking at the bigger picture, scientists have also observed a growing trend of storm clustering. In recent years, there's been an increase in the number of storms forming in quick succession during the hurricane season. This clustering can increase the likelihood that storms will interact with one another, possibly merging or creating more complex weather systems that are harder to predict and more difficult to prepare for. The current storm over the Atlantic could be just one part of a larger storm system that grows and evolves into something even more powerful as it interacts with other weather phenomena in the region. It's essential to understand that these patterns are not just one-off events. The combination of rising global temperatures, shifting jet stream patterns, and warming ocean waters is creating the perfect environment for storms to intensify faster, stay longer, and hit harder. The current storm forming over the Atlantic may very well be the first of many more storms to come as we enter an era of heightened atmospheric instability, making it all the more crucial for us to pay attention to these shifting patterns and how they could impact coastal regions and populations in the future. As we continue to examine the interconnected factors driving the intensification of storms like the one currently forming over the Atlantic, it's critical to look at the role that human-made infrastructure plays in exacerbating the effects of these powerful weather events. It's one thing to understand how natural forces, such as warming oceans and atmospheric instability, are contributing to the formation of megastorms. However, it's another to consider how the world's urbanization, deforestation, and even agricultural practices might be amplifying the devastation that follows. One of the most significant contributors to the heightened impact of storms is the rapid expansion of urban areas. Over the last few decades, populations in coastal cities and regions have grown substantially, often outpacing the development of infrastructure needed to protect them from natural disasters. In cities like Miami, New Orleans, and Houston, urban sprawl has led to the destruction of natural barriers that once provided a buffer against storm surges, such as mangrove forests and wetlands. These ecosystems naturally absorb excess water and reduce the intensity of storm surge flooding, but they are being replaced by concrete and buildings, making coastal cities more vulnerable to catastrophic damage. In addition to urbanization, the construction of massive seawalls and flood barriers, while helpful in some respects, has become a double-edged sword. These defenses may offer temporary protection from rising sea levels or storm surges, but they often fail to account for the complex and unpredictable nature of modern storms. They can also create a false sense of security, making populations complacent about the real risks they face. It's one thing to prepare for a typical hurricane season, but when storms are growing stronger and more erratic, these traditional defense systems may not be enough to protect against the full force of nature. Take, for example, the devastation caused by Hurricane Katrina in 2005. Despite the extensive levee systems designed to protect New Orleans from floodwaters, the storm surged over these barriers, leading to one of the most catastrophic failures of urban infrastructure in recent history. As the storm intensified, the levees that were supposed to keep the water out collapsed, flooding the city and causing widespread damage. It highlighted the limitations of relying solely on engineered solutions when it comes to protecting against increasingly powerful storms. Along with the loss of natural protection and the potential for infrastructure to fail under extreme conditions, another major factor exacerbating the impact of these storms is the global deforestation crisis. Deforestation, particularly in tropical areas, has a direct impact on storm formation and intensity. Forests, especially those in tropical regions, act as crucial carbon sinks, helping to regulate temperatures and stabilize weather patterns. When forests are cleared for agriculture, logging, or urban expansion, it disrupts the natural balance of the atmosphere. Trees absorb carbon dioxide, a major greenhouse gas that contributes to global warming, and without them, more heat is trapped in the atmosphere, fueling the intensification of storms. The Amazon rainforest, often referred to as the lungs of the earth, is particularly vital in regulating the climate and preventing extreme weather events. However, deforestation rates in the Amazon have reached alarming levels in recent years, weakening the ability of the rainforest to mitigate the effects of climate change. As the forest's capacity to absorb carbon decreases, the atmosphere becomes increasingly unstable, contributing to the intensity and frequency of storms. Additionally, agricultural practices have their own role to play in enhancing the destructive power of storms. When land is cleared for agriculture, it's often left barren, with little natural vegetation to absorb the excess moisture that these storms can bring. Soil erosion becomes a significant concern, as rainwater is no longer absorbed by healthy soil and instead runs off into nearby rivers, lakes, and oceans, contributing to flooding. The deforested and degraded land areas become prime candidates for rapid flooding, and the lack of plant cover accelerates the damage done by high winds and rain. One might wonder how this all connects back to the storm forming over the Atlantic, but these broader environmental changes are affecting the storm's behavior. The rising temperatures of the oceans and shifting atmospheric conditions are compounded by the disruption of natural ecosystems, creating an environment where storms are more likely to gain strength and wreak havoc. In places where human interference is greatest, these storms can make landfall with a fury that devastates infrastructure, destroys ecosystems, and leaves populations struggling to rebuild. Take, for example, Hurricane Irma in 2017. This storm was one of the most powerful Atlantic hurricanes ever recorded, and it caused unprecedented damage as it made landfall in the Caribbean and Florida. While it's impossible to attribute a single storm to human activity alone, scientists have pointed to the role of deforestation, greenhouse gas emissions, and the destruction of natural barriers as amplifying factors in the storm's strength. Coastal ecosystems that had been removed or damaged couldn't absorb the storm's surge, and urban areas were unable to cope with the scale of the flooding that followed. The global scale of environmental changes, from urbanization to deforestation and unsustainable agricultural practices, makes it clear that the problem is not isolated to one region or one storm. The storm forming over the Atlantic right now is simply one example of a much larger trend that we're seeing worldwide. As the planet warms and ecosystems continue to degrade, the conditions that support these powerful storms will only intensify, making future events even more devastating. It's critical for governments, communities, and individuals to address these challenges in a multifaceted way. Climate change mitigation, urban planning that accounts for storm resilience, and reforestation efforts are just a few steps that can help slow the intensification of these storms. While there's no quick fix, understanding the broader environmental context of these storms is key to mitigating their impact and saving lives in the future. By confronting both the natural and human-made drivers of storm intensification, we can begin to adapt to a world where extreme weather is no longer a rare anomaly, but an increasingly common threat that requires careful and thoughtful preparation. As we continue to unpack the deeper implications of how human activities are exacerbating the strength of storms like the one currently brewing over the Atlantic, it's important to recognize the broader environmental shifts that go beyond deforestation and urbanization. One key factor that cannot be ignored is the role of ocean pollution and its influence on storm development. While many focus on the carbon footprint of industries, transportation, and agriculture, the oceans themselves are undergoing significant transformations due to human actions. Pollution, particularly plastic waste, and toxic chemical runoff from industrial processes, are directly affecting the health of marine ecosystems. These pollutants alter the properties of seawater, affecting its temperature, salinity, and oxygen levels, all of which can play a role in storm formation. Marine ecosystems, such as coral reefs, are critical for maintaining ocean health and regulating temperature fluctuations. They act as natural barriers to wave action, reducing the intensity of storms and providing shelter to countless species that are vital to the oceanic food chain. However, coral reefs are rapidly disappearing due to pollution, ocean acidification, and rising sea temperatures caused by climate change. As these ecosystems die off, the ocean's ability to regulate temperature and stabilize local weather patterns diminishes, resulting in hotter seas that fuel storm development. In the same vein, the accumulation of microplastics in the ocean is another significant factor contributing to the intensity of storms. These tiny plastic particles, which have infiltrated nearly every corner of the world's oceans, can impact the natural cooling processes of the water. When microplastics are present, they affect the way sunlight interacts with the water's surface, potentially causing the water to retain more heat than it otherwise would. Warmer ocean surfaces directly correlate with the intensification of tropical storms and hurricanes, as heat provides the energy needed to drive the formation of these violent weather events. Furthermore, the pollution of the oceans with chemical runoff from industrial and agricultural processes creates toxic dead zones, areas of the ocean where oxygen levels are so low that marine life cannot survive. These dead zones, while seemingly unrelated to storm formation, can influence local weather patterns. As they grow in size, they disrupt the natural flow of currents and alter atmospheric conditions, making certain areas more prone to extreme weather events, including hurricanes and heavy rainfall. As we see the current storm over the Atlantic begin to form, it's impossible not to wonder how much these accumulated environmental stressors are contributing to its power. While the impact of ocean pollution on the storm's formation is still a developing field of research, early studies suggest a concerning link between polluted waters and the intensification of tropical storms. This research suggests that the increasingly polluted oceans are contributing to more frequent and more intense storms, potentially creating a feedback loop where the more powerful storms become, the more pollution is introduced into the oceans, and the cycle continues. Moreover, the practice of overfishing, which often goes hand in hand with pollution, contributes to the destabilization of marine ecosystems. The removal of vast quantities of fish from the oceans disrupts food chains and weakens the resilience of coral reefs and other critical marine habitats. The loss of these natural defenses makes coastal regions more vulnerable to the impacts of powerful storms, as they no longer have the same ability to absorb the force of waves and storm surges. The absence of healthy fish populations can also exacerbate the destruction of wetlands, further compounding the risks posed by storms like the one currently forming over the Atlantic. Interestingly, some scientists have also pointed to the warming of the Arctic as another indirect influence on storm formation in the Atlantic. The Arctic region has been warming at twice the rate of the global average, a phenomenon known as Arctic amplification. This warming is causing shifts in atmospheric pressure systems, which can alter the path and strength of storms. As the ice caps melt, they release fresh water into the ocean, disrupting the delicate balance of ocean currents and atmospheric circulation patterns. This, in turn, affects weather systems in the northern hemisphere, including storm patterns over the Atlantic. These atmospheric changes are contributing to the increasing unpredictability of storms, making them harder to forecast and prepare for. As the storm over the Atlantic intensifies, it serves as a stark reminder of the interconnectedness of natural systems and the ripple effects of human actions. The pollution of our oceans, the destruction of marine life, and the disruption of global weather patterns all feed into the creation of more destructive storms. It is no longer just a matter of preparing for hurricanes and tropical storms as we've known them in the past. We are now facing a new era of storms that are stronger, more frequent, and harder to predict. The solutions to these challenges are not simple. We need to shift our collective mindset and recognize that environmental protection isn't just about conserving forests or reducing carbon emissions. It's also about taking responsibility for the health of our oceans and marine ecosystems. Governments and industries must take immediate action to reduce pollution, protect marine life, and invest in sustainable practices that will help mitigate the intensity of future storms. Equally important is the role of individual responsibility. Small actions, like reducing plastic consumption and supporting sustainable seafood, can help alleviate the stress we are placing on our oceans. Public awareness and education on the interconnectedness of environmental issues are essential in fostering the collective action needed to combat these global challenges. Another factor contributing to the intensity of the storm forming over the Atlantic is a relatively lesser-known phenomenon: the disruption of the jet stream. The jet stream is a fast-moving ribbon of air high in the atmosphere that typically guides weather patterns around the globe. However, changes in its stability, due to both natural forces and human influence, are now being observed, and these shifts can have a dramatic impact on storm formation and strength. Over the last several decades, scientists have noticed that the jet stream is becoming more erratic. Normally, the jet stream flows in a relatively consistent pattern, helping to steer weather systems, including storms, in predictable directions. But as the climate warms, this powerful atmospheric current is being disturbed. The warming of the Arctic, in particular, has been shown to weaken the temperature contrast between the poles and the equator, which in turn weakens the jet stream. Without this contrast, the jet stream can become wavier, causing it to meander more than usual. What does this mean for storms like the one over the Atlantic? Well, a meandering jet stream can cause weather systems to linger for much longer in one area, including tropical storms and hurricanes. Normally, the jet stream helps to move these storms away from the coast, but a more unstable jet stream can cause these systems to slow down or even stall. When storms stall over warm waters, they have more time to gather strength and energy, growing exponentially stronger than they otherwise would. This disruption of the jet stream also means that storm paths can become erratic and unpredictable. For example, storms that might have moved out to sea in the past could now head directly toward coastal areas, leading to more severe storm surges, flooding, and damage. This is especially concerning because coastal communities are not only dealing with stronger storms, but also with more frequent storm impacts due to these changes in atmospheric circulation. To make matters worse, the wavy pattern of the jet stream can create blocking patterns, where storms get caught in certain regions for extended periods of time. This can lead to prolonged heavy rainfall or extreme heat in specific areas, which contributes to both the intensity of storms and the vulnerability of the affected regions. For example, in some cases, storms may become entrenched over warm ocean waters, drawing in moisture and heat for days or even weeks, creating a perfect storm scenario. Scientists are now grappling with how to predict the effects of these disruptions, as the jet stream's behavior is growing increasingly erratic and less predictable. Historically, meteorologists relied on more stable patterns to predict the course of storms, but with these shifts, the models they use are often no longer as reliable. As a result, many storms are hitting with greater intensity and more unpredictability, posing a greater risk to both the environment and human populations. While the causes of these jet stream disturbances are complex, there's no doubt that climate change plays a pivotal role. As greenhouse gases continue to warm the planet, the Arctic is warming at an accelerated rate, which is weakening the jet stream and causing the atmospheric currents to become less stable. Additionally, deforestation, pollution, and other human activities are contributing to atmospheric changes that further affect the jet stream's movement. It's a vicious cycle, one that is contributing to more dangerous weather events and intensifying storms like the one currently brewing in the Atlantic. As the jet stream continues to shift and weaken, experts are worried that the frequency of stalled storms, unpredictable paths, and prolonged weather events will only increase. The storm may not only be a result of rising ocean temperatures or air pressure shifts, but also of the increasingly chaotic atmospheric currents that govern weather patterns across the globe. What makes this cause particularly frightening is the fact that the jet stream is a high-altitude phenomenon, far above the Earth's surface. This means that many of the actions we take to reduce ground-level pollution may not be enough to directly impact the stability of the jet stream. It calls for more large-scale global efforts to address climate change at its root, from rethinking our energy systems to drastically reducing carbon emissions. In the meantime, the growing unpredictability of the jet stream poses a serious threat to regions vulnerable to storms. Governments, coastal communities, and individuals must adapt to the new reality of increasingly erratic storm systems. This might involve reinforcing infrastructure to withstand stronger storms, developing early warning systems that take into account shifting atmospheric currents, and investing in more resilient agricultural practices to handle more prolonged weather events. The connection between the jet stream and storm formation highlights a chilling reality. Our changing atmosphere is not just affecting the weather we expect, but it's also altering the very systems that guide those weather patterns. It's an intricate, complex web of environmental forces that, when disrupted, can create more powerful storms, less predictable weather, and a planet that seems to be throwing us new challenges every day. The storm forming over the Atlantic is just one symptom of a much larger issue, a reminder that the interconnectedness of our global climate system can have far-reaching, sometimes unpredictable consequences. As the storm intensifies over the Atlantic, another cause for concern is the phenomenon known as atmospheric rivers. These long, narrow bands of concentrated moisture in the atmosphere have been identified as one of the key contributors to the intensity of storms, especially in the case of tropical systems like the one currently developing. Atmospheric rivers are capable of transporting vast amounts of water vapor from the tropics to other regions, often dumping it in large quantities when they make landfall. What makes atmospheric rivers especially dangerous is their ability to feed into storms, rapidly intensifying them by supplying massive amounts of moisture. This is why many of the worst floods in coastal and inland areas can be traced back to the presence of these atmospheric rivers, which act as conduits for moisture, fueling storms to a degree that significantly increases the threat of extreme rainfall, flooding, and even landslides. When combined with the warming ocean temperatures we've discussed earlier, atmospheric rivers can provide the supercharger effect, turning already potent storms into catastrophic weather events. Researchers have been studying how atmospheric rivers are changing in response to climate shifts, and the findings are unsettling. As ocean temperatures rise, the atmosphere holds more moisture, creating conditions ripe for atmospheric rivers to become more frequent and intense. In a sense, the warmer the oceans, the more moisture is available to these rivers, and the more powerful the storms that they feed. The result is not just stronger storms, but storms that can reach much farther inland, affecting regions far beyond the coastlines that are typically more prepared for storm-related impacts. The strength of atmospheric rivers is measured by their ability to carry large volumes of water vapor. Some of the most extreme examples can carry as much water as the Mississippi River, if not more. This water vapor is then released in the form of heavy rainfall or snow once the atmospheric river reaches land. For the Atlantic storm, this could mean a sudden deluge that could overwhelm local drainage systems, cause widespread flooding, and strain emergency services to their breaking point. And with coastal cities already battling rising sea levels and higher storm surges, the impact of this added moisture could be devastating. One of the reasons atmospheric rivers have such a profound impact on storm behavior is because they are often slow-moving. This gives the storm time to gather strength, as it can continue to feed off the moisture for hours or even days. By the time these atmospheric rivers make landfall, they've accumulated enough water to cause massive rainfall events. Cities that are typically not affected by heavy rains may suddenly be faced with weeks of continuous downpours. The sheer volume of rainfall can overwhelm flood defenses, turning normal storm systems into something far more catastrophic. This intensified rainfall, paired with the storm's existing momentum, can lead to even more severe outcomes. The more moisture that is available to a storm, the stronger the winds can become as well. A storm that starts off as a tropical depression may quickly evolve into a full-blown hurricane or a superstorm if the atmospheric river continues feeding it. The result is a storm that moves with alarming speed, picking up energy and strength from both the ocean and the atmosphere, leaving communities along its path with little time to prepare. The changing climate is contributing to a shift in how atmospheric rivers behave. As more data becomes available, scientists are finding that these moisture-laden systems are not just becoming more frequent, they're also extending farther into previously unaffected regions. In the case of the Atlantic storm, this could mean that areas previously considered safe from direct impacts may be at risk. Places like the southeastern United States, which typically face hurricane threats, could now experience more frequent inland flooding, while areas in the Northeast and even parts of the Midwest, far from the storm's initial landfall, could see record-breaking rainfall. What's more, the interaction between atmospheric rivers and other storm systems is still an area of ongoing research. Atmospheric rivers have the potential to merge with tropical storms or hurricanes, dramatically increasing the severity of the storm. The combination of moisture-rich air from the atmospheric river and the high winds of the hurricane can create a feedback loop that perpetuates storm intensity. For example, once a tropical storm starts to pull moisture from an atmospheric river, the increase in moisture can enhance the storm's convection, allowing it to strengthen and grow larger. One real-world example of this phenomenon occurred during the 2017 Hurricane Harvey disaster. As the storm approached Texas, it encountered an atmospheric river stretching from the Pacific Ocean, dumping unprecedented rainfall over the state. What started as a typical hurricane became one of the most devastating floods in U.S. history, with some areas receiving more than 50 inches of rain. The role of the atmospheric river in this storm's intensification and prolonged rainfall was a key factor in the destruction it caused, and experts are now concerned that such occurrences could become more common in the future as the planet warms. Scientists are racing to understand exactly how atmospheric rivers will evolve with the changing climate, as well as how their increased intensity could interact with other meteorological factors to create storms of unprecedented magnitude. What we know for sure is that this process is far from predictable, and the growing unpredictability of storms like the one brewing over the Atlantic is something that is worrying experts more and more. As this storm feeds on the moisture from atmospheric rivers and the warming oceans, its path and strength could continue to change, creating an even greater challenge for the communities in its way. The lesson here is clear: We must brace for storms that are not only more powerful but also more difficult to predict, as the interactions between the atmosphere, oceans, and atmospheric currents grow increasingly complex. As the storm continues to grow over the Atlantic, it becomes increasingly evident that the role of atmospheric rivers is only one part of a much larger, more complex system of factors contributing to the severity of the storm. One aspect that is often overlooked but plays a crucial role in the development of massive storms is the shifting dynamics of the jet stream. The jet stream is a high-altitude, fast-moving band of air that circulates around the globe, playing a key role in determining weather patterns. But, as global temperatures rise, scientists have observed that the jet stream is weakening and becoming more erratic. A weaker jet stream means that storms are no longer being steered with the same efficiency as in the past. Instead of moving rapidly across the Atlantic, storms may slow down and become stationary, causing them to dump enormous amounts of rainfall on the same areas for extended periods of time. This can lead to catastrophic flooding, as we've seen in various cases throughout history. Additionally, when storms stall in one location, they can become more organized and powerful, as they continue to draw in moisture and energy from the surrounding environment. This phenomenon is not just a theoretical possibility, it's already happening in real time. One example can be drawn from 2019 when a stalled weather system in the Gulf of Mexico combined with a weak jet stream, resulting in catastrophic flooding across the Midwest United States. A similar dynamic could be in play with the current storm brewing over the Atlantic, as it interacts with the weakened jet stream. If the storm becomes stationary or moves at a slower pace, it would give the storm more time to strengthen and intensify, making it a far more dangerous and unpredictable event than initially expected. The link between the weakening jet stream and extreme weather events is something that researchers are still working to fully understand. However, what we do know is that this shift in atmospheric circulation patterns is making it more difficult to predict where storms will land and how long they will last. In the case of our current storm, this could mean that coastal areas, which are typically prepared for the passing nature of hurricanes and storms, may be forced to endure prolonged periods of dangerous weather. Cities like Miami, New Orleans, or even parts of the Caribbean, which usually experience relatively quick hurricanes, could face longer, more drawn-out events. The uncertainty in the storm's trajectory, coupled with the unpredictability of its intensity, leaves communities with less time to respond and make necessary evacuations or preparations. Another critical element in the storm's potential severity is the interaction between the storm itself and the ocean currents below. The storm's energy is not just coming from the surface temperature of the ocean, it's also being amplified by the way in which the storm interacts with the deeper ocean currents. The Gulf Stream, a warm ocean current that flows from the Gulf of Mexico up the eastern coast of North America, plays a significant role in fueling hurricanes. The warmer the Gulf Stream waters, the more energy is available for the storm to draw upon, allowing it to grow exponentially. What makes this particularly dangerous in the context of a storm like the one forming over the Atlantic is the potential for the Gulf Stream to become even warmer due to the ongoing rise in global temperatures. This warming process is another manifestation of climate change, which not only affects the temperature of the ocean's surface but also influences the deep water currents. As the Gulf Stream warms, it could potentially feed a storm with an unprecedented amount of energy, allowing it to rapidly intensify and shift into an even more powerful system. The result would be a storm that isn't just large but incredibly destructive, with the capacity to produce hurricane-force winds and torrential rainfall that could stretch hundreds of miles inland. And unlike other types of storms, the Gulf Stream's ability to supply energy could make it last longer, potentially leaving affected areas in a state of emergency for days or even weeks at a time. This danger is compounded by the fact that many coastal regions and island nations, especially in the Caribbean, rely on early warning systems to help prepare for approaching storms. But with the rapid intensification made possible by the storm's interaction with the Gulf Stream, these systems may be overwhelmed or simply too slow to issue adequate warnings in time. The storm could evolve so quickly that communities would have little time to act, causing widespread devastation before authorities can even issue proper evacuations. It also highlights the challenge of forecasting storms with such complexity, as the changing dynamics between atmospheric factors, oceanic currents, and storm systems make it harder for meteorologists to pinpoint exactly when and where the storm will hit hardest. In the event of such rapid intensification, the storm's track could become more erratic. Hurricanes and tropical storms tend to follow certain patterns, moving in more predictable paths as they are guided by atmospheric currents. But when a storm draws so much energy from warm ocean currents like the Gulf Stream, it can deviate from its usual trajectory, potentially affecting regions that were originally thought to be safe from direct impacts. The unpredictability of this process is another factor contributing to the growing anxiety surrounding the storm. The storm's interaction with the ocean's currents and the weakening jet stream paints a picture of a future where storms become more difficult to track, more intense, and more dangerous. We are already seeing the beginning of this shift, as the storms of today are becoming more extreme than those of the past, and it raises the crucial question: how do we prepare for a future in which these storms are more frequent, more unpredictable, and more destructive? As we look ahead, it's clear that we must rethink our approach to disaster preparedness and response. Communities that are located in storm-prone areas, like coastal cities or islands, will need to invest in better infrastructure to handle extreme weather events. These places will also need to develop systems that can better anticipate and respond to rapidly intensifying storms, ensuring that evacuation procedures and resources are available in time for everyone to get to safety. The need for better early warning systems that take into account the complex interactions between the atmosphere, ocean currents, and storm systems is becoming more pressing than ever. What's more, it's clear that climate change is only going to exacerbate these challenges. As we continue to see temperatures rise and ocean currents shift, storms like the one forming over the Atlantic are likely to become more common. These changes in the environment are not just affecting the storms themselves, they are also creating an atmosphere of uncertainty and fear, as people are left wondering when the next massive storm will hit and where it will land. The storm we're currently tracking may be a sign of what's to come in the future, and it's crucial that we start adapting now before it's too late. Let's now shift our focus to another potential cause of this gigantic storm forming over the Atlantic, the role of El Niño. Known for its disruptive influence on global weather patterns, El Niño is a climate phenomenon that involves the warming of ocean waters in the central and eastern equatorial Pacific. Typically, El Niño events disrupt typical atmospheric conditions, causing changes in global weather, such as more intense hurricanes in the Atlantic, droughts in some regions, and heavy rainfall in others. El Niño has been linked to some of the most destructive storms in history. The most notable of these events occurred in 1997 to 1998, when the phenomenon created one of the strongest El Niño events on record. During that period, a series of devastating hurricanes and tropical storms formed in the Atlantic and Pacific Oceans, leaving widespread destruction in their wake. But why exactly is El Niño such a potent factor when it comes to the development of massive storms? To understand this, we need to look at how El Niño changes the ocean atmosphere system. Under normal conditions, trade winds push warm surface waters from east to west across the Pacific Ocean. This results in an area of cooler waters in the central and eastern Pacific, which supports the development of hurricanes and storms. However, during an El Niño event, these trade winds weaken or even reverse, leading to the accumulation of warm water in the eastern Pacific. This warming creates a dramatic shift in atmospheric pressure and circulation patterns. With the central Pacific waters heating up, the typical climate systems that influence the Atlantic are thrown off course. Normally, the cooler waters in the Atlantic's tropical regions serve to suppress hurricane formation by limiting the amount of moisture and heat that can fuel the development of storms. But during El Niño years, the warmer waters in the eastern Pacific can shift atmospheric pressures, making it easier for storms to form in the Atlantic. Essentially, El Niño reduces wind shear, which is the difference in wind speed and direction at various altitudes. Lower wind shear is one of the key ingredients in the formation of powerful hurricanes because it allows these storms to grow without being torn apart by strong winds at higher altitudes. What's more, the presence of an El Niño pattern can shift the paths of storms. Hurricanes that would typically move westward toward the Caribbean or the Gulf of Mexico may instead be steered toward the eastern United States, particularly along the eastern seaboard. This is because the altered wind patterns during an El Niño event can push storms away from their usual routes, making their trajectories more unpredictable. In the case of the storm forming over the Atlantic, an ongoing El Niño could be contributing to its unexpected behavior, encouraging it to grow larger and shift its path toward regions that are usually less affected by such storms. Beyond just altering wind patterns, El Niño also influences the amount of moisture available to storms. With the central Pacific's waters warming up, the amount of moisture in the atmosphere increases, which can fuel more intense rainfall. This influx of moisture can turn an already large storm into a catastrophic deluge, as seen in 1982 to 1983 when an El Niño event led to devastating flooding across parts of the world. In this context, the current storm over the Atlantic may be intensifying due to the extra moisture provided by El Niño, feeding into its already volatile and unpredictable behavior. It's also worth noting that El Niño has long-term effects on ocean temperatures. As the warm waters from the Pacific shift toward the Atlantic, this not only increases the surface temperatures of the Atlantic Ocean but also affects the deeper ocean currents. When the ocean's surface heats up, it can create a feedback loop, where more heat is transferred into the atmosphere, intensifying the storm. Additionally, the warmer ocean temperatures can make storms more powerful and longer lasting, especially if they remain over warmer waters for an extended period. This amplification effect creates a storm system with the potential to grow rapidly, become more destructive, and last longer than usual. In essence, the warming of the Atlantic's waters, augmented by El Niño, could lead to an atmospheric system that amplifies the storm's strength, making it much harder to predict and much more dangerous for any region in its path. Furthermore, the presence of El Niño has been correlated with shifts in storm season timing and intensity. In the years when an El Niño event occurs, hurricanes in the Atlantic tend to be more powerful, but fewer in number. However, the storms that do form are often much more destructive, with stronger winds and heavier rainfall. This means that even if the current storm over the Atlantic is the only one to form, its strength and impact could be far more intense than anything expected during a typical storm season. When all of this is taken into account, it becomes clear that the storm's potential threat is not just based on its immediate characteristics. Rather, the storm is a manifestation of a much larger and more complex system at work. The influence of El Niño, in combination with other factors like ocean currents, atmospheric pressure, and climate change, creates a perfect storm scenario where multiple ingredients come together to form a potentially catastrophic event. And as this storm continues to evolve, experts are keeping a close eye on the El Niño phenomenon, knowing that it could provide the perfect environment for the storm to intensify in ways that would be difficult to predict. Whether it shifts course or strengthens into something even more formidable remains to be seen, but the combination of factors, some of which are human-driven, will certainly continue to shape the storm's future path. As we continue to observe the development of this storm, it's crucial to understand that the interactions between El Niño and the other atmospheric factors are just a small piece of the larger puzzle. While experts work to predict its behavior, the power of these interconnected climate systems shows us how little we truly know about the future of storm patterns. The continued unpredictability of these events underscores the importance of being prepared for the unexpected and knowing that these storms could become more frequent and more intense as our planet continues to change. As we continue to observe the ongoing developments of the storm forming over the Atlantic, another key factor to consider is the role of climate change in exacerbating these extreme weather events. While the phenomenon of El Niño itself is naturally occurring, human-driven climate change has the potential to intensify its effects, leading to even more severe storms. Over the last few decades, global temperatures have been rising steadily, largely due to the increase in greenhouse gases like carbon dioxide and methane, which trap heat in the atmosphere. This shift in global temperature has a profound impact on weather patterns, and hurricanes and storms are no exception. One of the most significant ways in which climate change influences storm intensity is through the warming of ocean temperatures. The heat that accumulates in the ocean is a critical energy source for storms, particularly hurricanes. Warm ocean waters act as the fuel that powers these storms, causing them to intensify as they move across the sea. As the planet warms, so too does the surface temperature of the oceans, providing an ideal breeding ground for larger and more destructive storms. This is one of the reasons why experts are increasingly concerned that hurricanes are becoming more powerful, and why the current storm over the Atlantic is being taken so seriously. Recent studies have shown a clear trend. Warmer ocean temperatures correlate with stronger and more frequent storms. For example, the 2005 Atlantic hurricane season, which included the infamous Hurricane Katrina, was one of the most devastating on record. Scientists attributed the strength of these storms to unusually warm sea surface temperatures in the Atlantic Ocean, a direct result of global warming. Similarly, the hurricane season of 2017, which saw storms like Hurricane Harvey and Hurricane Irma wreak havoc across the Caribbean and the United States, also coincided with elevated ocean temperatures. The current storm in the Atlantic is being watched closely not only because of its potential size and intensity, but also because of its timing. It comes at a moment when ocean temperatures are at some of their highest levels ever recorded, a trend that could mean the storm will continue to gain strength as it moves forward. In addition to higher sea surface temperatures, the warming atmosphere can hold more moisture, which means that storms can generate heavier rainfall, leading to catastrophic flooding. These heavier rains can overwhelm cities and infrastructure, compounding the effects of the storm's winds and making the aftermath even more challenging to deal with. What's more, the rise in ocean temperatures due to climate change can also affect the frequency of storms. While El Niño and La Niña typically operate in cycles, the long-term trend of warming oceans has the potential to disrupt these cycles, leading to more frequent and unpredictable weather events. This could mean that storms like the one forming over the Atlantic may become more common in the future, with even less time to prepare for them. The unpredictability of these events is what makes them so dangerous, as we are seeing with the current storm. It's not just about tracking its path. It's about understanding how global climate changes are altering the conditions that give rise to these massive, destructive storms. The impact of climate change on these storms also extends beyond just their intensity and frequency. As the climate shifts, we are witnessing a change in the typical locations where storms form and make landfall. For example, the warming waters of the Atlantic are now reaching further north, which means that storms that typically stayed in tropical regions are now moving into more temperate zones, affecting areas that are not accustomed to such extreme weather. The storm brewing in the Atlantic could potentially move toward regions in the northern parts of the United States, Canada, or even Europe, making it a highly unpredictable and dangerous force to reckon with. Moreover, the rise in global temperatures also affect atmospheric pressure systems, which in turn influence storm behavior. The warming of the Earth's surface creates more unstable atmospheric conditions, contributing to the formation of more intense low-pressure areas, which are the precursors to powerful storms. This feedback loop of rising temperatures and changing atmospheric conditions could lead to storm systems that behave in unexpected and unpredictable ways, with the potential for rapid intensification and large-scale destruction. In addition to the direct impact on storm intensity, climate change is also influencing how long these storms last. With more available energy in the atmosphere and oceans, storms may not only intensify more quickly but also endure for longer periods. This prolonged activity can lead to sustained damage, as communities may be dealing with the effects of the storm for days or even weeks, rather than just a few hours. For example, Hurricane Dorian, which struck the Bahamas in 2019, stalled for an extended period over the region, intensifying while moving slowly and causing catastrophic flooding and wind damage over the course of days. This kind of extended storm activity is becoming more common as climate change amplifies the underlying conditions that fuel these systems. While the storm in the Atlantic may seem like a singular event, it is part of a larger, interconnected system influenced by climate change. As the climate continues to warm, we can expect storms to become more powerful, more frequent, and more unpredictable. The consequences of this are not just limited to the destruction caused by the storms themselves, but also the long-term effects on infrastructure, economies, and communities. Cities and regions that were once considered safe from these types of events are now finding themselves in the path of storms that they were never prepared for. This shift in storm behavior emphasizes the need for global action to address the underlying causes of climate change, as well as improved preparation and mitigation strategies for the storms that we know are coming. As we continue to examine the role of climate change in the formation and intensification of storms, it's crucial to understand the broader atmospheric dynamics at play. One significant factor is the changing patterns of wind currents and ocean currents, which are closely linked to global warming. These currents are responsible for distributing heat and moisture across the globe, and their disruption can have profound effects on weather systems. The warming of the oceans, as mentioned earlier, is changing the behavior of these currents, which in turn is influencing the development of storms over the Atlantic. For instance, the Gulf Stream, which is part of the Atlantic Meridional Overturning Circulation, AMOC, plays a vital role in regulating the climate of the North Atlantic region. This current moves warm water from the Gulf of Mexico up towards the northern latitudes, while cold water sinks and flows southward in a continuous loop. However, recent research suggests that the Gulf Stream has been weakening due to the melting of the polar ice caps, which has introduced a significant amount of fresh water into the North Atlantic. This influx of fresh water is reducing the salinity of the ocean waters, which in turn impacts the density and movement of the water, causing the Gulf Stream to slow down. A weakened Gulf Stream has a ripple effect on the entire climate system. For one, it reduces the amount of heat transported from the equator to the northern latitudes, leading to cooler temperatures in places like Western Europe. But more importantly, it disrupts the normal circulation patterns in the atmosphere. This shift can lead to changes in the jet stream, which controls the path of storms. When the jet stream becomes unstable, it can cause storms to linger longer in one place, intensifying as they do so. It also contributes to the increased frequency of extreme weather events, such as heat waves, droughts, and of course, intense storms like the one currently forming in the Atlantic. The weakening Gulf Stream is just one example of how the disruption of ocean currents due to climate change is playing a pivotal role in altering storm behavior. With these changes, storms are not only becoming more powerful but also more erratic and difficult to predict. For instance, when the Gulf Stream weakens, it can cause high-pressure systems to become more persistent, leading to prolonged periods of calm weather, followed by rapid intensification of storms when they do eventually form. This erratic storm behavior is troubling for forecasters, who rely on established patterns to predict storm paths and intensities. In addition to the impact of ocean currents, the overall increase in atmospheric moisture due to global warming is another factor that exacerbates the severity of storms. Warmer air holds more moisture, and this can lead to heavier precipitation as storms develop. When a storm forms over the Atlantic, the rising warm air can draw vast amounts of moisture from the ocean's surface, turning the storm into a potent rainmaker. As the storm moves inland, this excess moisture can lead to flash flooding and dangerous rainfall totals, overwhelming flood control systems, and putting communities at risk. Take Hurricane Harvey, for example. In 2017, it dropped a staggering 60 inches of rain in some areas of Texas, leading to catastrophic flooding. Scientists have argued that the warming atmosphere allowed for such an extreme amount of moisture to be absorbed by the storm, making it much more destructive than it would have been otherwise. As global temperatures continue to rise, the likelihood of storms like Harvey intensifying in this way becomes more of a reality. The storm currently developing in the Atlantic could be another example of this pattern, potentially bringing devastating rainfall totals and widespread flooding. The impact of increased moisture on storm behavior is also linked to another key issue, the warming of the polar regions. As the Arctic warms faster than any other part of the planet, it disrupts the balance of atmospheric circulation and can lead to more extreme weather events. The loss of sea ice in the Arctic contributes to the destabilization of weather patterns in the northern hemisphere, creating an environment where storms can become more powerful and erratic. The reduced ice cover in the Arctic means less sunlight is reflected back into space, which further accelerates warming in the region. This warming, in turn, affects the jet stream and other atmospheric currents, which can trigger more severe storms as they move across the globe. The changes in the Arctic also influence the location and intensity of storm systems. As the Arctic warms, the temperature difference between the poles and the equator becomes less pronounced, weakening the pressure gradient that drives weather systems. This can cause the jet stream to meander, allowing storms to travel in unusual patterns or stall over certain regions, causing prolonged periods of extreme weather. The storm over the Atlantic, which is being closely monitored, may be an example of this very phenomenon. If the jet stream becomes unstable, it could lead to the storm intensifying quickly or changing course in unexpected ways, further complicating efforts to predict its impact. As we explore the various factors contributing to the formation of this massive storm over the Atlantic, it's clear that climate change is influencing not only the intensity of storms but also their behavior, frequency, and unpredictability. With warmer oceans, changing atmospheric patterns, and more moisture in the air, storms are becoming increasingly dangerous and harder to predict. The storm we're tracking is a perfect example of how these global shifts in climate are altering the nature of extreme weather events, and the concern among scientists is growing. While we may not yet fully understand the exact impact of all these factors combined, what is certain is that the world is facing a new era of more intense and unpredictable storms. And this is just one example of how climate change is altering the landscape of extreme weather events. As we continue to monitor the storm's progression, it's essential to remember that the larger question is not just about tracking one event, but understanding how these changes are reshaping our planet's weather systems. As we come to the end of our deep dive into the massive storm forming over the Atlantic, it's clear that the forces shaping these extreme weather events are more complex than we ever imagined. What we're witnessing is not an isolated occurrence, but rather a reflection of the broader shifts happening in our planet's climate system. The warming oceans, shifting wind patterns, melting ice caps, and increased atmospheric moisture are all playing a part in making storms more powerful, unpredictable, and frequent. These changes are forcing us to rethink how we prepare for and respond to extreme weather. Every storm we track is a potential reminder of the fragile balance we're living in, where a single event could have far-reaching consequences, both in terms of human impact and environmental disruption. As the world continues to warm, we are confronted with an unsettling reality. Our old systems of predicting and preparing for storms may no longer be enough. What we thought we knew about weather patterns and storm dynamics is being turned upside down. And while the storm we're watching over the Atlantic may be the one making headlines today, similar events are likely to become more common in the years to come. The unpredictability of our climate has already altered the way we look at storms, but it's also prompting a larger question: what can we do to mitigate the impact of these changes? How can we adjust our infrastructure, our early warning systems, and our responses to the new realities we're facing? Experts around the globe are sounding the alarm about the need to address these challenges head-on. There's no quick fix, but awareness is the first step toward making necessary adjustments. From understanding the deeper causes of these storms to preparing ourselves for what lies ahead, the urgency is undeniable. With every new storm that forms, there is an opportunity to better understand the evolving nature of our planet's weather systems, and to push for more effective solutions that can help minimize damage and save lives. As we continue to track the storm and monitor its development, we must remain vigilant. These storms are not just acts of nature, they are a warning sign of something larger at play. The way we respond today will shape the future of our planet for generations to come. If you want to stay updated on this storm and the other extreme weather events happening around the world, be sure to subscribe to our channel. We'll be here, tracking these events and breaking down what they mean for the future. Stay informed, stay safe, and remember, the more we understand, the better equipped we'll be to face what lies ahead. So, hit that subscribe button and join us for more updates and insights on the world's most pressing weather phenomena.